I had this question passed on to me by Tom, so I thought perhaps that would be a good opportunity to record it while I'm answering this question. So if I don't get things wrong, I hope we can make it through this question together. This is particularly a very interesting question because it kind of makes use of all the rules of sets that we learned so far. And also, we can perhaps make use of Venn diagram as well at the same time. So let's just examine what the question is asking us. Events A, B, and C are defined in a sample space. So they have given us the probability of A, they've given us the probability of B, the intersection of A and C, and also the union of B and C. Now we have to take note of this because it says that probability of A and B are mutually exclusive. So if I wanted to draw this as a since they are mutually exclusive, A and B should be totally separate regions. They can't have a shared area or an intersection. And B and C are independent. Now, the independence can't really be shown in a diagram. Independence is more a inherent aspect of a probability. So if a probability depends on another probability, then of course they're not independent. So for example, if a team winning is dependent on the weather, so their probability of winning will be different if it rains and if it doesn't rain. So it could, in that case, it is not independent. But in this case, they're independent. So really, the occurrence of one before the other one doesn't affect it. Now, so I think perhaps because they haven't told us where C is, we could assume that C may have some shared areas with B and C, but A and B for sure don't cross in any way. Okay, well let's get the first part done. So the first part says, what's the probability of B knowing that C has happened, or sometimes given? So this straight line here is thought of as given. So if prior to B, C has happened, what would be the probability of B? Well, the probability of B will not be any different. Okay, so probability of B will not be any different because B and C are independent. So therefore, probability of B given C is occurred is actually no different to the independent probability of B because B doesn't depend on C. So in fact, the answer for the first part is probability of B, which is 0.2, is just in the question there. Okay, now finding probability of C. Finding probability of C. They've given us the union. They've given us the intersection. So I wonder if that intersection is any use here. So the intersection of A and C. So the intersection of A and C will just be here, won't it? So that will be 0.04. And we already know the probability of A. So probability of A would be all of that. Now, since we already know that that's 0.04, so the rest of it would be 0.36. Yeah. Now, probability of C. We got the union, so let's use the union formula. Now, I'll just show you some of the formulas. So we do use these formulas quite regularly. So let's make this a bit smaller. So let's see how many of these formulas we know. So we know that the union, we're going to use this actually. The union of A and B is equal to the sum of the two probabilities A and B, but taken away from it the intersection of them. Because when you union A with B, we are actually counting the intersection part twice. So we need to take that part away. And since we're talking independence here, the probability of an independent situation would be A times B. But if two probabilities depend on one another, then if A happens before, it will have to be multiplied by probability of B, not solo B, but B knowing that A has happened before it. Because that probability, if it's dependent, if it's not independent, then that would be different with just B by itself. So I think I'm going to use this one. So let's shrink this and put it on the side so we can keep an eye on what we're writing. I'm gonna write it here. So we know that the probability of B union C is 0.44. So probability of B union C is equal to probability of B plus probability of C minus probability of B and C. Yeah. So I'm just really using I'm using this here. Now, since B and C are independent, it means that probability of B and C is just equal to probability of B times C. So 0.44, which is the value that they had given us. So if you go back to the question, you can see they actually had given us this value. So that would be equal to probability of B, which was 0.2, I believe. Probability of B of 0.2 plus probability of C, which we don't know. So let's call that one X. I don't know. And then minus the probability of B times by probability of C. That's just the intersection. So probability of B is 0.2, probability of C we don't know. So let's just write that one more time. So 0.44 is equal to 0.2 plus X minus 0.2. So that's 0.2. So 0.2 times X. Yeah. So that's really 1x, take away 0.2x. So that would be, the equation would become 0.2 plus 0.8x. So if I take this to the other side, 0.24 is equal to 0.8x, which means x, which we substituted for P probability of C, x would be equal to 0.24 divided by 0.8, which makes 0.3. So that's the probability of C. So all of that is 0.3. B and C now can be found because B and C is 0.2 times by 0.3. 0.2 times by 0.3. That's B and C. So 0.2 times 0.3 makes 0.06. 0.06. So that's altogether 0.1. The whole thing was 0.3. So it gives us 0.2 here. And B was 0.2. So B is all of that, 0.2. So if we take that away from it, it leaves us 0.14. Okay. Now, so I'll bring the question in again, since we already have some information. about. So I'll bring the question again. Okay, so we already know what B and C is. B and C was 0.2 times 0.3, which was 0.06. Now this one is the complement rule. So let me just show you that rule. If you need a copy of these set of rules, just drop me a line. I've got these as PDF files. I could just send them to you. And so the complement says that if you have an intersection being knotted, so knot of an intersection is basically knot of each item. So it's just knot has been brought in. So it will be knot of each one of these, and then intersection becomes union. And the same thing applies here. All of these can be shown and explained to you, but I think because I just wanted to get this answer done. If you need any one of these, Tom, if you need any one of these explained, then I can actually prove to you that these works. These rules do work. And so an intersection of a union would be and knot of a union is the knot of each item with union change into intersection. Now they have that, so that's really this situation, and we can turn that into this. Yeah. So in fact this is equivalent to probability of A union B union C not. So all of these added together. So if I go back to the picture, this without the knot, this thing without the knot would be all of these added together. So if we add all of these together, that makes 0.4, and that makes 0.2, so that's 0.6, and 0.2 makes 0.8. So all of these make 0.8. So in fact, the probability of just the unions is 0.8. So that would be 1 minus 0.8, which is 0.2. So that's the outside of the union. So outside of the union, so union is all of these together. Not of that, which is the outside of that, is here, which is 0.2. So that was actually much easier to do than doing the intersection of each knots. So knot of A, knot of B, knot of C, and intersection of them. So I think union is easier to do. So you get the union of all of them, and then you knot it. The last part might be easy to do using the Venn diagram, because we are looking for C and not B. But we can also use a formula. So using a diagram, C and not B. So not B is everywhere that is outside of B. Yeah. And so it's everything that is outside of B, all of these areas that is outside of it. Intersection with C mean intersecting it with whatever is C. So the intersection part is only these two. So it will make 0.24. Yeah. So outside of B is everything that is outside of B. So that includes this, and this. Intersection with B. So the only bit that is actually in intersection with C. So the only place with C is these two that can intersect with, and so therefore 0.24. But we can do this as a formula, and I think the formula might be interesting. I'm going to use this here. So we are wanting to find the probability of C and not B. If I add the probability of C and B, so these two are the complemented parts. Hence, the sum of these two would give you the probability of the bit that hasn't been complemented. Yeah. Let me move this out of the way. So C. Okay. So we already know what probability of C was. Probability of C was 0.3. Probability of C and B was 0.06, which means the bit that we are looking for would be, so this bit that we're looking for would be that taking away that side. So that would be 0.3, take away 0.06. So X, or in fact the probability of C and B naught, is equal to 0.24. Yeah, so that's using formula. So using a picture, if I just quickly use the picture again. So we were looking for, intersection of B naught. So I'm going to do the B naught in green. So that's B naught. B naught is the green area. Yeah. Intersection with C. So I'm going to do the C in blue. So this is C. So intersection, which is an and, intersection is where both colors are together present. So the only area that both colors together are present is this area here, which is the 0.4 and 0.2. Okay, well, drop me your questions. I've got to go back to finishing the work with Tom, but that was a bit that was necessary to maybe be recorded and put on for the rest of you guys to use it. And so I'll see you in my next video.